In this video, we're going to discuss the second conic section, the so-called hyperbola. So we're going to find that the equation of a hyperbola looks very similar to the equation of an ellipse, but their graphs look radically different. So a hyperbola is formally defined as the set of all points in the plane such that the difference, in other words, we're looking at subtraction, the difference in distances between these points, the points representing the graph, and two fixed points, the so-called foci, we're familiar with that term now, is a positive constant. So when we defined an ellipse, we had a very similar definition to this, except that we were looking at points whose sum of their distances was the same from the two foci. In this case, we're taking the difference of the distances between each of the points on the graph and the two foci. So when we graph something based on that formal definition, this is going to be the graph that we get. So notice in this case we have two foci, but they're going to be, in this case, outside of what we're going to think of as the vertices. So just as an ellipse has foci and vertices, a hyperbola does as well, but it looks very different from what we see with the ellipse. So with the ellipse, the foci are always going to be closer to the center of the graph than the vertices are, and in the case of the hyperbola, that's actually going to be flipped. So the general idea is if we look at any point and take its distance from the two foci and then take the difference of those two values, then we find this constant value that is consistent for all of the points on the graph. So the reason we have the type of graph we do, we have the shape we do, look at what we're essentially drawing right here. Essentially we're drawing a little triangle that goes from the actual graph to each of the foci and then passes along that line that connects the two foci. Well, you can imagine drawing that triangle in actually four different ways. So if we were to reflect across this axis, we could draw the same triangle and we'd end up with a matching point down here, which gives us this particular shape. But also, if we were to look at a point that's closer to this focus and then further away from this focus using the same two distances, then we end up with a matching triangle and matching points on this particular side as well, which forms this portion of the graph. So that's the reason we end up having the graph that we do. But as with ellipses, it's going to be more important that we just recognize how we find all of these key features of our graph rather than focusing on this formal definition so much. So as you notice, the hyperbola consists of two portions on its graph, what we call the branches of the hyperbola. So two separate branches. And then the line segment that passes through the foci is what we call the transverse axis. So with an ellipse, we have a major axis and a minor axis. With a hyperbola, we have a transverse axis. So it's going to pass through the foci, through the center of the graph, and also it terminates at the two vertices. So technically it's not actually going to pass through the foci, but it's going to be collinear with whatever line the foci are going to lie on. So it connects our two vertices, which are essentially the closest together points if we look at the two branches of the graph. And then the midpoint of the transverse axis is going to be the center of the hyperbola. So notice in this case, the center is between the two branches of the graph, whereas if we were looking at the ellipse, it's inside the actual graph. Also, the vertices, again, are closer to the center than the foci are. The foci are going to be further away, contained one within each of the two branches. So we actually see hyperbolas in real life, believe it or not. So if you've ever seen power plant cooling towers, nuclear power plants have them, some coal burning power plants have them as well. The edges of a cooling tower are roughly hyperbolic. So that particular curve and then the matching curve on the other side forms a hyperbola. Also, the edges of an hourglass are hyperbolic, and then we have a center in the middle. Also, if you've ever seen one of those, I don't know what you would necessarily call it, but you put a coin in a slot and it rolls down a funnel around in a circle until it falls into the bottom of the funnel. That's what we call a hyperbolic funnel. So that particular shape is also based on the shape of a hyperbola. So now let's talk about how we would identify a hyperbola and how we identify the features of its graph in order to get an accurate graph. So just as with ellipses, we're going to focus both on graphs that are going to be centered at the origin as well as graphs that have a shifted center that is no longer the origin. So we're also going to define values A, B, and C, just like we did for ellipses. They're going to mean slightly different things here, just based on the form of the equation that we look at. So we're going to let A and B both be positive numbers. Now notice I'm not saying that A is greater than B in this case like we did with the ellipse, and we'll see why in a minute. A versus B is going to be defined in a different way in this case. So we either have a horizontal hyperbola, which means the transverse axis is along the x-axis. That means the branches are oriented horizontally from one another. Or we can have a vertical hyperbola, which means the transverse axis is vertical, in this case along the y-axis, which means the branches are distributed vertically from one another. So a horizontal hyperbola centered at the origin is going to take on the following form for its equation. So x squared over a squared minus y squared over b squared is equal to 1. So you'll notice it's almost identical to the equation for an ellipse with one major difference. We've changed from addition to subtraction. So the subtraction is what's going to make the difference here. As soon as we have a quadratic term minus another quadratic term, that's our indication that we're looking at a hyperbola. And in this case, A is going to be associated with the positive term, and B is going to be associated with the negative term. So if we're looking at a vertical hyperbola, you can probably guess what's going to happen. It's the same kind of thing that happened for an ellipse. In this case, we're focusing on y squared first, and then x squared. And notice in this case, I didn't change which one I referred to as A and which one I referred to as B. In this case, A is associated with y and B is associated with x. So when we're talking about a hyperbola and we're talking about A and B, A is always going to be associated with the denominator of the positive term, which could be x squared or y squared depending on what we're looking at. And then B is always associated as the denominator of the negative term, be that again y or x. So that's going to make the determination for what A versus B is. So keep in mind, B could be the larger value in this case. All we're focused on is which of the two values is associated with the positive variable, x or y, depending on the situation we're looking at. So again, in both of these cases, we are centered at the origin, which means our transverse axis is going to pass through the origin. Now we also need to define a value for C, and just as the equation for a hyperbola is a little bit different from the equation for an ellipse, the associated value for C is a little bit different as well. So again, it almost looks the same, except C for an ellipse, we have a squared minus b squared, whereas C for a hyperbola, we have a squared plus b squared. I just always remember it as you need to have the pair, subtraction and addition. So in the standard form of an ellipse, we have addition within the actual equation, so the value for C involves subtraction, whereas with a hyperbola, our equation involves subtraction, so our value for C involves addition. And in this case, C is going to be larger than our two values. So when we looked at an ellipse, we noticed that C was going to be smaller than A in this particular case, so that the foci were closer to the center than the vertices were. In this case, the foci are going to be further out than the vertices, which means C is going to be larger than our value for A in this case. So based on that, our foci are going to be distributed again from the center of the graph. And essentially we find them the same way. So if we start at the center and we're talking about something that's distributed horizontally, we go C units to the right from the center, C units to the left, but notice we're not changing the y value, so we're holding the y value constant and just altering the x value to find our foci. So the coordinates for the foci are going to be c, 0, and negative c, 0, if we're talking about a horizontal hyperbola. Now, if we're talking about a vertical hyperbola, we're looking at foci that are above and below our center. So c units above, c units below, which means we're keeping the x value constant, and then we're adjusting the y value using this value of c, which means our foci have coordinates 0, c, and 0, negative c. And this looks the same as it does for an ellipse. It's just a different value of c. We're finding c in a slightly different way. Now our vertices are also determined in the same way, in this case using the value for a, but remember a isn't necessarily going to be the larger of the two denominator values. It's just based on which denominator is associated with the positive term, be it x squared in the case of a horizontal hyperbola or y squared in the case of a vertical hyperbola. So in terms of our vertices, it's going to be a units away from our center, distributed horizontally if we're talking about a horizontal hyperbola. So again, we're going to hold our y value constant at 0 and then just adjust our x value. So our vertices are going to have coordinates a, 0 and negative a, 0. And then for our vertical hyperbola, it's going to be opposite. So our vertices are above and below our center. We hold the x value constant and just adjust the y value using our value for a. So our vertices are going to have the coordinates 0, a and 0, negative a. Now, when we talked about an ellipse, this was the point where we talked about the minor axis, the fact that we had something else as part of our graph to help us determine the full shape of the graph. So just having horizontal values or just having vertical values isn't enough. We need something that gives us another direction as well, so we get the whole structure of the graph. As far as a hyperbola is concerned, this is where our asymptotes are going to come into play. So believe it or not, you've actually graphed hyperbolas before. They just didn't look exactly the way they look right now. So for instance, if you've ever graphed anything related to the reciprocal function, which is f of x is equal to 1 over x, that particular graph also is the graph of a hyperbola. It's a hyperbola that is neither horizontal nor vertical. It has a diagonal axis, but the structure is the same, and what we notice the first time we graph something like that is that it has what we refer to as asymptotes. So asymptotes are going to be these imaginary boundaries that our graph does not cross, but that give our graph a particular shape. So when we look at a hyperbola, our hyperbola consists of two asymptotes that happen to intersect, in this case, at the center of the graph. And as we graph the actual branches of the hyperbola, they're going to follow the shape that's given by these asymptotes. So the equations of the asymptotes are going to be the additional piece of information we need in order to get the full picture. So asymptotes in this case are linear, so the equations we write are going to be in slope-intercept form. So we're going to have two of them, which means there's two equations. I'm going to write it as the form of just one with a plus minus though. So my asymptotes are going to be of the form y is equal to plus or minus b over a times x. And then if I'm looking at a vertical parabola, it's going to be y is equal to plus or minus a over b times x. Now, how do we determine which one's going to be the numerator and which is going to be the denominator? That's based on which value goes with y and which value goes with x. So we know the value in front of x, if we're talking about something linear, represents our slope, change in y over change in x. So our numerator is always going to be the value associated with y. So in this case, the value associated with y was assigned to the letter b. And in this case, the value associated with y was assigned to the letter a. And then our denominator represents change in x, so the value assigned to x was a, and in this case the value assigned to x was b. So just think whatever's associated with y over whatever is associated with x. And if we split this up into two equations, one with a positive value, one with a negative value, that's going to give us our two asymptotes. Okay, so before we actually graph, let's talk about an actual approach to graphing. So again, the branches of the hyperbolas are bounded by our two asymptotes, in other words, confined within them, given shape by them. And then graphing a hyperbola can be simplified by focusing on key features, including these asymptotes. So number one, the center. Where's the graph centered? Number two, the vertices. Think of the vertices as the starting point for each of the two branches. And then the asymptotes. So if we know where the graph is centered, we know where the asymptotes intersect. If we know where the vertices are located, we know where the branches of the graphs begin. And then if we know the actual asymptotes, we know how the actual branches of the graph are going to emanate from those vertices. So knowing those key features, those three key features, is going to give us the graph we need. So what we're going to use to graph is what we call the box method. The hardest part to graph is going to be the asymptotes. Once we have the asymptotes graphed, it's really just a matter of filling in everything from there. So when we graph a hyperbola, number one, we're going to identify our center and our vertices. So once we know where our center and vertices are, of course, we're going to plot those on the coordinate plane. And then the next step is to draw a rectangular box with a particular size. So it's going to be centered at the very center of the graph, and it's going to have dimensions 2a and 2b. So 2a represents the distance from one vertex to the next, and 2b is going to give us the vertical distance. Just like having the major versus the minor axis gives us something horizontal versus vertical, or vice versa if we're talking about something that's vertical. Having these two values, that's going to give us essentially the structure for how we graph those asymptotes. So once we have this box drawn, hence the term the box method, we're going to draw the asymptotes through the opposite corners of the box. And if we've drawn the box correctly, those two asymptotes are going to pass through the center, and they're going to be structured in such a way so that we can just trace out the graph of the hyperbola by starting at each vertex and then following the asymptotes. So let's look at a couple of examples. And just like with the ellipses, we want to identify all those key features that we need and then put everything on the graph and see if we can get a reasonably good picture. Now you'll probably want to have some type of straight edge with you so that you can draw those asymptotes a little bit more easily. So we want to identify this hyperbola's center, its vertices, its foci, and its asymptotes, and then graph the hyperbola. So just like with an ellipse, it's a good idea to start by just identifying A, B, and then finding C. So remember, A is not necessarily associated with the larger of the two denominators. It's associated with the denominator of the positive term. So first off, because our positive term is the term involving x, automatically that tells us we're looking at a horizontal hyperbola. In other words, our branches are going to be distributed from one another horizontally. And it also means our transverse axis is going to be horizontal. Okay, so based on that, A is going to be the square root of this denominator. So A is not 4, A squared is 4, which means A is going to be 2. And then B squared is the denominator associated with the negative term, which is going to be 9. So B is going to be 3. So C is defined as the square root of A squared plus B squared in this case. So 4 plus 9, which is the square root of 13, so an irrational number. And we encountered this quite often with ellipses. Sometimes the value for C ends up being irrational, even though the values for A and B are pretty easy to graph. Okay, so the center for our graph, where we start the graph, is going to be the origin just based on the form for our equation. Now, because we're talking about a horizontal ellipse, let me go ahead and put the center on here. Because we're talking about a horizontal ellipse, we know the foci are going to be distributed away from the center horizontally. So C units to the right and C units to the left, which means we're holding our y coordinate constant. Okay, so starting from the center, maintaining the y coordinate of the center, the foci, the two foci, are going to be C units away to the right and to the left, which means we have foci at square root of 13, 0, and negative square root of 13, 0. Okay, now those are going to be a little bit harder to graph, but as with the ellipses, what we really need to be able to graph, those are going to be the points that are actually on the graph. Foci are used to generate the graph, but they're not actually points that are truly on the graph of the two branches of the hyperbola. What we really need to graph, those are going to be the vertices. So the vertices, again, are going to be horizontally distributed away from our center. In this case, A units to the right and A units to the left from that center. Okay, so A in this case is 2, so we're going to hold our y value constant again, and then adjust the x value. So 2 units to the right, and then 2 units to the left of our center. And those will be actual points on the graph, so I'm going to add those to the graph. There we go. So the center will not truly be on the branches of the graph. These 2 points will. So the question then is, how do we draw the branches accurately from there? That's where the asymptotes are going to come into play. So our asymptotes are going to be of the form y is equal to positive or negative. Now we need to decide how we're going to orient these two values. So remember, the slope of a line is always going to be the change in y over the change in x. So we're going to take the value associated with y. In this case, that's our value for b, so it's going to be 3. So the numerator of our slope is going to be 3. Divided by the value associated with x. So that's going to be 2 in this case. Now don't make the mistake of using 9 over 4. Remember, those are a squared and b squared. We're looking at a and b for generating the actual components of the graph. And so that's going to be the general slope, and then that's going to be multiplied by x. So it's worth writing out the actual 2 separate equations. So that's y is going to be positive 3/2 x, and y is going to be negative 3/2 x. Now, technically speaking, we could graph these just the way we normally graph lines. In this case, these are 2 lines in slope-intercept form. They have a y-intercept of 0, and these are their 2 slopes, so we could generate additional points using that particular idea. However, the way we're going to graph our asymptotes is using the box method. So the box method says, centered here at the center, we want to draw a rectangular box around the center that's 2a units wide, and in this case 2b units tall. So we already have the width of the box because we already have a units distributed in either direction. So this is going to be the width of the box, the distance to go from one vertex to the other vertex. Now in terms of the height of the box, that's where we're going to use b. So here's how I recommend you do this. B was 3, okay, so from the center, the height of the box is going to be 2b. In other words, 3 units above, and then 1, 2, 3 units below. So what would this look like if we drew a box that had those dimensions? Well, the edges of the box are going to pass through the actual points that we plotted. So here's the highest point on the box, here's the lowest point, which means passing through the vertex, we're going to have a side of the box that looks like that. And then we're also going to have a side of the box, I think I went a little bit too far. There we go. That looks like that. Okay. And then the width of the box, also going to pass through those particular values. And I apologize if it's a little bit hard to see using the pen. I'll make sure to graph the actual graph using a marker. There we go. There's our box. So let me darken that in just a little bit, just so it's a little bit easier to see. Thicken all of those lines just a little bit. There we go. Now that's a little bit easier to see. Okay, so that is going to be our guideline for drawing our asymptotes. So if we draw diagonal lines that pass through each pair of opposite corners, then we essentially have our asymptotes. And I'll make sure to draw these with a marker. So I'm going to line up my straight edge so that it passes through a pair of opposite corners. And then I'm going to draw my asymptotes. Now, keep in mind, asymptotes are imaginary. They're not really there. So the traditional way to draw asymptotes is using a dotted line. So I'm going to draw a dotted line representing each of these two asymptotes. And notice again, they're going to pass through the center, and they're also going to pass through the two corners of the boxes, of this particular box. Okay. And so what I'm currently drawing is going to be the asymptote that had a positive slope, and then the previous asymptote I drew was the one that had the negative slope. So there are our two asymptotes. So all we need to be able to graph the hyperbola now is to start from our vertex, from either of our two vertices, and follow the shape that those asymptotes give us. And I like to draw just one side at a time. So we're essentially going to have something that looks like that above. It looks like that below. And then we have a mirrored branch on the other side of the box. And there we go. So there is our graph. Now, to be clear, the asymptotes are imaginary and the box is also imaginary. The actual graph for the hyperbola is that pair of matching branches, those mirrored branches. So we have to keep in mind when we draw things like the box, when we draw things like the asymptotes, it's important to indicate that they're not really there and make sure that it's clear what is actually part of the graph. And in that case, it's those two branches right there. Okay, let's look at another example. And I apologize for the glare on the paper. It's just the right time of day to have a little bit of glare. Okay, so we have 16y squared minus 9x squared is equal to 144. So we encountered an example similar to this in the last section when we looked at ellipses. This equation represents a hyperbola, but it is not in standard form. One of the main reasons why it's not in standard form is this 144 on the right-hand side. We want to have a 1 over there, and then we want to have a denominator for each of these two terms. It's more important that we have the 1 though. That's the focus here. So in order to get a 1 and keep the left-hand side structured the way we need, we're going to take that 144 and we're going to divide it out from all three terms. So we have 16y squared. We're going to divide that by 144 minus 9x squared. We're going to divide that by 144. And that's going to be equal to 144 divided by 144. And so if we simplify all of that down, we're looking for common factors that would divide into 144 and 16. Well, let's see if 144 is divisible by 16. Certainly it is in this case, so that's going to reduce to y squared over 9. And then if 16 goes into 144 9 times, then 9 goes into 144 16 times. So that's going to give us x squared over 16, and then that's equal to 1. So that is going to be our standard form. That's what we're going to base our A, B, and C on. Now A is always associated with the denominator for the positive term, which is the y term in this case. So if the y term is our positive term, that means we have a vertical graph. It means the branches of our hyperbola are going to be distributed vertically from one another. Our transverse axis is going to be vertical. Okay, so a squared is going to be 9, which means a is going to be 3. B squared is going to be 16, which means b is going to be 4. And c is going to be the square root of a squared plus b squared. So 9 plus 16, which is the square root of 25, which is 5. Okay, so once we have those three values, we have everything we need to find all of the components of our graph. So our center is still at the origin, 0, 0. And then our foci, let's think about this. So here's our center. Our foci are distributed in this case, c units above and c units below our center, which means we're holding our x value constant and then adjusting the y value c units above, c units below the center. So the x coordinates of our foci, those are still going to be 0, but the y coordinate is going to increase and decrease by c, which is 5. So we have a focus at 0, 5, and a focus at 0, negative 5. So 0, 5, and 0, negative 5. And if we want to graph those, we can. In this case, let's just graph them just to see how they relate to the actual branches we're going to graph. So 0, 5, and 0, negative 5. Okay, now more importantly, the vertices, the 2 points that are actually on the branches of the graph. So in this case, we're going to be a units above the center and a units below. So again, holding our x coordinate for our center constant, and then the y coordinate increases and decreases by a value of a. So we have vertices at 0, 3 and 0, negative 3. So let's put those on the graph as well. And I'm going to draw those points a little bit larger just so we don't forget those are the actual values that our graph is going to pass through. So the center and then the two foci, those are in a sense imaginary. They're not truly on the graph. They're used to help us draw the shape of the graph, but these two vertices are points that are actually on those two branches. Okay, and then last but not least, let's find our asymptotes. So y is equal to positive or negative. Find the slope, okay? So it's always going to be the value associated with y divided by the value associated with x. So in this case, a is associated with y and b is associated with x. So that means I'm going to take 3 divided by 4, and that's going to be used to generate my slope. And so if I split that up into two equations, that's going to be y is equal to 3/4 x and y is equal to negative 3/4 x. Okay, and again, we could draw those by hand, or we can use the box method and essentially generate those in a slightly more artificial manner. So we want to draw the box centered at this center that has dimensions 2a vertically and then 2b horizontally. So we've already got the height of the box. Now b is going to be 4, so that means we're going to go out 4 units to the right and 4 units to the left in order to generate the other values for the box. So out 4 units to the right and then out 4 units to the left. So we have a height of 2a and then a width of 2b, and that's going to give us the box. So where are our corners going to be? We're going to have a corner right here, we're going to have a corner right here, and then a corner here, and a corner here. So I'm just lining up the points, drawing the rectangle from there. So let's see if I can make this box a little bit easier to see in this case. That's looking a little bit better than last time. Okay. Now just for the sake of verifying, how do we know that this box is really drawing our asymptotes correctly? Well, let's think about what would happen if we graphed these two lines. So each of these lines has a y-intercept at 0, so we'd be starting from the center. And then suppose we wanted to graph y is equal to 3/4 x, which means we have a rise of 3 and a run of 4 to get from any point to any other point on the graph. So from our y-intercept, if we rose 3 and ran 4, notice where we end up. We end up at a corner of the box. So if we were to connect those points, which also have to connect with this bottom corner, then we draw that asymptote. Now same kind of thing for the other one. It has a y-intercept at 0, and then a rise of -3, if we want to think of it that way, and then a run of 4. So rise -3, and then run +4. And again, not a coincidence, we end up at a corner of the box. And so if we connected those dots, we also have our other asymptote. So that's why the box is going to work the way it does. Essentially, it generates the components of our rise and run, just in a little bit easier way than having to do it by hand. So let's connect our dots. Remember, the asymptotes are not really there. They give us the shape for our graph, but they are imaginary lines, just these imaginary boundaries that bound our branches for these hyperbolas. Okay, so once I have those, now it's just a matter of filling in our graph. Now we've got a lot of points on here. Where are our vertices? We're talking about a vertical hyperbola, and these are our two vertices. So each branch of the hyperbola is going to emanate from one of the vertices. So here's branch 1, and then the branch below. So that's going to be, roughly speaking, our hyperbola. So that gives us a couple of examples of how to graph a hyperbola that's centered at the origin. Now, what happens when the center of our graph shifts? What happens when it's no longer centered at the origin? Well, essentially what we saw with ellipses is going to be consistent for hyperbolas in terms of how we make adjustments, just based on how things are related to the center of the graph. Just like with ellipses, the formulas are going to get a little bit more complicated. But in terms of graphing, it's going to be easier to graph if we really understand the structure of what we're looking at. How are things distributed away from the center of the graph? Rather than trying to focus on memorizing formulas for each of these components, focus on starting with the center and then distributing things out either horizontally or vertically away from the center. Okay, so we're going to define A and B in the same way, but now we have a new center other than 0, 0. Our new center is going to be the ordered pair H, K. So a horizontal hyperbola, where our transverse axis is horizontal, that is now centered at H, K, is going to take on the following form. It's going to be x minus h squared divided by a squared minus y minus k squared over b squared is equal to 1. Now, if our hyperbola happens to be vertical, essentially the y term is going to be positive, the x term is going to be negative, so these are going to switch. So y minus k squared, and then that's now going to have the denominator of a squared since it's the new positive term, minus x minus h squared over b squared. All of that is equal to 1. Okay, so just as with ellipses, we have to pay very close attention to what's actually here in the standard form. So notice h and k are being subtracted. That means if we truly see subtraction in our standard form equation, then h and k, the actual values, have positive signs. If instead we see an addition, we think of an addition as being subtraction of a negative value. Since the subtraction is part of the standard form, addition is subtraction of a negative value, which means we'll have coordinates that are negative. Now past that, the focus is still defined in the same way in terms of C, but now we're distributing away from a new center, not 0, 0, but h comma k. So again, let's think about what this would look like. So if we have a horizontal hyperbola, we've got a new center at h comma k, wherever that happens to be. The focus is going to be C units to the right and to the left of our center. Okay, so we're keeping the y value constant, and we're just adjusting the x value by C units in either direction. So now our x and y are no longer 0 and 0, they're h and k. We're holding the y value constant, and we're just adjusting h by C units to the right and C units to the left. So our foci are going to be h plus c, and then hold the y value constant, and then h minus c, and then hold the y value constant. Now, if we're looking at a vertical hyperbola, our foci are above and below our center. So we're going to hold our x value constant and then just adjust the y value by C units. So h is going to be held constant, and then k is going to increase by C units, so k plus c, and then it's also going to decrease by C units, so k minus c. So those are going to be our foci. Those are going to be the points that are inside of the branches of our hyperbola. Now the vertices are structured essentially the same way, except we're now adjusting our values by a, whatever a happens to be. So if we're looking at a horizontal hyperbola, the vertices are a units to the right and to the left of our center. So again, hold the y value constant, and then the x value adjusts positive a and negative a units. So the vertices are going to be h plus a, hold the y value constant, and then h minus a, hold the y value constant. If we're looking at a vertical hyperbola, the vertices are a units above and below. So hold the x value constant, adjust the y value, positive and negative a units. So hold the x value constant, and then add on a units, hold the x value constant, and then subtract a units. And then our asymptotes are going to adjust as well. So essentially what we're going to end up with is something that looks like not slope-intercept form, but point-slope form, which can then be put into slope-intercept form. What really changes is how we write the y and the x. So if y has a k subtracted and x has an h subtracted, essentially think of just subbing those particular expressions in where we previously had just a y and just an x. So our asymptotes are going to be of the form y minus k is equal to positive or negative. Okay, we need the slope. So the value associated with y is going to be b. The value associated with x is going to be a. So that's going to be b for change in y, a for change in x, times, now not x, but x minus h. So just as before, that still represents two actual equations, one where we have positive b over a, one where we have negative b over a. Once we look at each of those, we can then move things around, we can distribute that b over a, we can add this k, move it over, and we can put that into slope-intercept form. But that's going to be the simplest way of writing it before we have actual values in place. And then same thing for our vertical hyperbola. So y minus k, and then we have our slope. So in this case, a is associated with y, and b is associated with x. So change in y, which is a, change in x, which is b, times x minus h. And again, same kind of thing. This is actually two equations in one. We can split those up, positive and negative. We can distribute the slope. We can move the k over. We can put those into slope-intercept form. Now with these particular equations, it's going to be much more important that we understand how the box method works, because accurately graphing the asymptotes once they're in this form is going to be more challenging. So using the box method to graph is going to make our lives a lot easier. It's going to make graphing those asymptotes a lot easier. So let's look at an example. Okay, so we have negative x minus 2 squared over 9 plus y plus 3 squared is equal to 1. Now, does this truly represent a hyperbola? It looks like maybe it does, maybe it doesn't. This doesn't look exactly like the standard forms we just saw on the previous page. But notice we have two quadratics. We have a quadratic x, a quadratic y. Okay, so that's a good sign. We have 1 on the other side, and we have a term that's positive, and we have a term that's negative. So the fact that they're not both positive is what differentiates a hyperbola from an ellipse. But in this case, essentially, these have just been written out of order. So if this makes us uncomfortable to see this kind of thing, we'll just rearrange it. We can rearrange that. Typically, we write the positive term first. So y plus 3 squared would come first. And then we write the negative term. So x minus 2 squared over 9, and then that's equal to 1. Now it almost looks like maybe we're still missing something because we don't have a denominator over here. Well, remember, anytime you have something that doesn't have a denominator, the denominator is really 1. So we really have a denominator of 1 associated with our y term. And now we're in the standard form for a hyperbola, and we can determine our a, b, and our c from there. Okay, so a is going to be associated with the positive term. Okay, the positive term in this case is the y term, which means we're looking at a vertical hyperbola, so branches above and below the center. Okay, so that means a is going to be the square root of this value, which happens to still be 1 in this case. And then b is going to be the square root of 9, which is going to be 3. So c is going to be the square root of a squared plus b squared, which is the square root of 10. So again, in this case, we have an irrational value for c, but that's okay, because we're not really going to have to graph using c. Okay, so what is our new center, though? As soon as we see anything added or subtracted directly from x and y, that represents a shift in the graph. Okay, so from x, if we want to look at this form, we have x minus 2, which means the new x coordinate is not negative 2, but positive 2. The subtraction is part of the standard form equation, so subtraction of a positive number. Y, on the other hand, we've added on 3, which means subtraction of a negative 3. So our true center is going to be 2, negative 3. So let's put that on the graph. So 2, negative 1, negative 2, negative 3. Now remember, that's not actually on the branches, but it is truly the center. So the branches are going to be distributed from there. And since we're looking at a vertical hyperbola, we have a branch above that, we have a branch below that. Okay, now let's find our foci. So we're talking about a vertical hyperbola. So the foci are going to be above and below the center by c units. So if we're going above and below, we're not adjusting x, we're just adjusting y. So for the foci, the x coordinate is going to be held constant. So we have an x coordinate of 2, and then the y coordinate is the one being adjusted. We go c units above and c units below. So one y coordinate is going to be negative 3 plus the square root of 10, and then one y coordinate is going to be negative 3 minus the square root of 10. And of course, if we wanted to actually graph those, that's where you plug those two irrational values into your calculator, you get approximations, and you can graph in that manner. Let's focus on the vertices, though. Okay, so the vertices are also distributed away from the center in the same way. If we're talking about a vertical hyperbola, if this is our center, we've got a vertex above, we've got a vertex below, a units in either direction. So we're holding our x value constant, And we're just adjusting our y value, increasing by a units and decreasing by a units. So -3 plus or minus 1. I'll just write it that way and then we can break that up. So -3 plus 1 is going to be -2. So we have a vertex at 2, -2. And then -3 minus 1 is going to be -4. So our other vertex is at 2, -4. So let's put those on the graph. So 2, -2, and then 2, -4. Notice they are equidistant from the center, and if we take the distance between them, that's going to be 2 units, which is 2 times a, which is going to be the height when we draw the box to represent our asymptotes. So, asymptotes, let's look at those. Now don't stress about these, it looks like it's getting more complicated, but all you really have to remember is where you had y and x, you're now going to substitute y plus 3 and x minus 2. So in that summary form, we have y plus 3 is equal to plus or minus, okay, now we need the slope. So which value is associated with y, which is associated with x. In this case, y was the positive term, so a is associated with y, which means we have a 1 for our numerator, and then b is associated with x, so we have a 3 for our denominator. And then where we would normally have an x, we now have x minus 2. Now, for purposes of simplification, we do need to split those up. We can't distribute in the form that we're in. We absolutely have to split those up and simplify one at a time. So our two equations are y plus 3 is equal to 1/3 times x minus 2, and y plus 3 is equal to -1/3 times x minus 2. And then we want to put each of those into slope-intercept form so that the equations are a little bit more meaningful. So we're distributing our 1/3 and then moving the 3, distributing -1/3 and then moving the 3. So start with the distribution. So we have y plus 3 is equal to 1/3 x, and then 1/3 times -2 is going to be -2/3. Okay, same thing over here. I'm going to do one step at a time on each side. So y plus 3 is equal to -1/3 x, and then those two negatives make a positive, so +2/3. So the next thing we have to do is subtract the 3, move it over, combine with the other constant in order to isolate y, same thing on the other side. Now let the calculator do the hard part for you. You don't actually have to do that algebra by hand. So for the left-hand equation, we're taking -2/3, okay, and from that we are subtracting 3. So we have a decimal form. Let the calculator convert that to a fraction for you, which is going to keep you from making a silly mistake just in your arithmetic. So on the left-hand side, we have y is equal to 1/3 x minus 11/3. That's going to be one of our equations. So our y-intercept is -11/3, and from that we use the slope of 1/3 to find additional points. Now same thing over here. Now we have a +2/3, so 2 divided by 3, okay, and then from that we are subtracting 3. And then we can convert that back to a fraction, and that's going to give us -7/3. So our other equation is y is equal to -1/3 x minus 7/3. So a y-intercept of -7/3 and then a slope of -1/3 to find additional points and graph that line. Now graphing these two lines accurately would be difficult, mainly because our y-intercepts are fractional and we don't have fractional grid lines. We just have grid lines along our integer values. So graphing these accurately and thereby getting the hyperbola accurately would be difficult. Here's where the box method really comes in handy. So remember, the box method requires us to draw a box around the center that has 2a units in one direction and 2b units in the other direction. So we already have a height of 2a, so 1 unit below the center, 1 unit above, there's the height. We also need a width of 2b, so b units in either direction away from the center. So 3 units to the right, and then 1, 2, 3 units to the left, which means our actual corners are going to be like that. So from there we can draw our box, and that is going to give us what we need to graph our asymptotes. Okay. So give me just a minute. Oops. Apologies, I can't seem to hold the ruler steady. There we go, that's better. Okay, so there's our box. So through the corners of that box, we draw our asymptotes. So the first asymptote, the one I have positioned right now, that's going to be the one with the negative slope. And notice when we actually look where it passes through the y-axis, it doesn't pass along the actual grid. It passes somewhere between the grid lines, which we know would occur because we have a fractional y-intercept. Let's graph our other one. And again, notice it actually passes through the y-axis at a fractional location, not along the actual grid. And again, that's because we also have a fractional y-intercept for that particular line. So we follow those asymptotes passing through our vertices. And that is going to be our hyperbola. So not majorly different. Ultimately, the hardest part here is just finding those components, finding the vertices, finding the foci. Past that, drawing the box is really fairly straightforward. Okay, so let's look at one final example similar to this one, not from the standpoint of graphing, but we also investigated another issue when we talked about ellipses. What happens when we have an equation that technically represents an ellipse but doesn't look like it? So as with ellipses, an expanded hyperbolic equation, one that's not in standard form, can be converted to standard form by completing the square. Okay, so how would we even know we're looking at an equation that represents a hyperbola? Well, what we're really looking for are a quadratic x and a quadratic y. We want those to be the highest exponents on x and y. And we're also looking for the fact that one of those terms is positive and one of those terms is negative. Now, if they were both positive, that's our indication that we're looking at an ellipse. The only thing that changed in terms of the equation to go from an ellipse to a hyperbola was the fact that we now had subtraction involved. One term was positive and one was negative. So if we see an expanded form that's quadratic in x and y, and one of those two terms is negative, that's our indication that we're looking at a hyperbola. And just like with ellipses, we can use completing the square to put our hyperbolic equation in a standard form, something that would be easier to graph. There's one additional consideration here, though, that we have to be careful about. It's not really going to change our strategy or our approach. It's more of an issue that just we need to be aware of. We need to be aware that when we are grouping x and y terms, when we're rearranging things, grouping the x terms, the y terms, the terms that have to go together, we have to take into account that one squared term is negative. Grouping is a little bit riskier when we're grouping something that has a negative term. We have to be very, very careful with our signs. So I'll show you what that looks like when we get to that point in the problem. Okay, so we want to write the equation of this hyperbola in standard form. And we're going to take the same approach as we did before. So first thing I want to do, move my 75 over, so I only want variable terms on the left-hand side. And I also want to go ahead and rearrange terms so that my x's are grouped together and my y's are grouped together. And I'm not going to put parentheses in yet, I'm just going to rearrange and then move that 75 over. So the x squared term is positive, so I'm going to keep that out front. We have a positive 66x. Okay, and then we have a negative 2y squared. We have a negative 4y. And then we're moving that 75 over by subtracting, so we now have a negative 75 on the other side. So I now want to group the terms that go together, so the x terms and the y terms. Now, grouping the x terms is not a problem because the quadratic x term is positive. Now, when I group the y terms, I'm going to keep the negative with my 2, and I'm going to change it into an addition of that grouping. So I'm going to keep the negative with the 2 because negative is part of the y squared coefficient. What if I hadn't done that? What if I'd left the negative out front and then just grouped around the 2? Well, technically speaking, I could do that, but I have to take into account that when I group, I'm saying that that negative applies to everything in parentheses. Well, if this 4 is also negative, and we're saying a negative applies to the whole set of parentheses, we would actually have to adjust the sign for the 4 to make it positive. Essentially, by leaving the negative out, we've factored out a negative from both of these two terms. We'd have to adjust those two signs to make them both positive to indicate that any negative out front is impacting both of those terms. So it's a lot safer just to group including the negative with the particular coefficient on that quadratic term. Because then when we factor, we can take care of the negative in that situation. So once we get to this point, we're going to factor out the coefficient for each of those squared terms. So I'm going to factor out an 11. That leaves me with x squared plus 6x. And here I'm going to factor out a negative 2. So that becomes a minus 2. And then we need to be careful here. So we're factoring out a negative 2 from the negative 4y. We factored out the negative, so that leaves us with a positive 2y. And particularly for this second set of parentheses, it's not a bad idea just to at least mentally redistribute and make sure that you get back to where you started. So negative 2y squared, negative 4y, so that factorization makes sense. And then I still have negative 75 on the other side. I haven't actually added anything new, I've just rearranged and grouped things in my equation. So now is where I complete the square. So just as a reminder, we're going to look at the linear term, and specifically we're going to look at the coefficients 6 and 2. So to complete the square, we're going to take that linear coefficient, we're going to divide it by 2, and then we're going to square it. And that's going to be what we add into parentheses to complete the square to give us a trinomial that factors in a certain way. So 6 divided by 2 is going to give me 3. If I square it, that gives me 9. So inside the first set of parentheses, I'm going to add a 9. We'll worry about the other side in just a moment. Now I need to do the same thing for my second set of parentheses. So I have y squared plus 2y. I'm going to take the linear term, divide it by 2, which will give me 1, and then square it, and 1 squared is going to give me also 1. Now, at this point, I have changed the left-hand side of the equation, so I need to balance it by repeating those actions on the right-hand side. So we've added a 9 and a 1, but not quite. We've really added an 11 times 9 and a negative 2 times 1. So both of those values also need to be added in on the other side. So we've added an 11 times 9, and we've also added a negative 2 times 1, or we can think of it as subtracting a 2 times 1. And so that's going to balance out everything left to right, which keeps the same structure. So now I have what we refer to as perfect square trinomials. They factor as a binomial that's repeated or a binomial squared. So that's going to give me x plus 3 squared, and then y plus 1 squared. And then on the other side, I just need to clean all of that up. So we have negative 75 plus 11 times 9 minus 2 times 1. And that's going to give me 22. So last but not least, we need to get the 1 that we like to have on the right-hand side for standard form, which means I need to divide out a 22 from all of my terms. So divide the 22 on the left to keep things in balance, divide the 22 on the right to get the 1 that we need. And notice the 11 and 22, the 2 and 22, those are going to reduce. So 11 and 22 reduces so that I have a 2 in the denominator. And then the 2 and 22 reduce so that I have an 11 in the denominator. And 22 over 22, as desired, reduces to 1. So this is going to be our standard form. All we were asked to do in this case was to put it in standard form, but of course at this point we could find our new center, so that would be negative 3 and negative 1. We would have a horizontal hyperbola, because the x term is the squared term, is positive, and then we can find a and b based on our two denominators. So in the next video we're going to look at our last type of conic section, the parabola. So we've looked at ellipses, we've looked at hyperbolas. We noticed that the two equations look very similar when we have an ellipse versus a hyperbola. The only difference is the sign in our equation. So if both of our quadratic terms are positive, we know we have an ellipse. If one of the quadratic terms is positive and one is negative, we have a hyperbola. And clearly that negative sign makes a major difference in terms of how the equation graphs. Now when we look at a parabola, the one major difference is that we only have one quadratic term. So more than likely you've graphed parabolas before. You've probably only graphed parabolas where x was squared. So when we look at parabolas, we're going to generalize a little bit more. We're going to look at situations where x is squared as well as situations where y is squared.